let's just talk a little bit about pressure. This will give you a little bit more background so you can start to think about the next lab experiment. So pressure is defined as the force per unit area. So it's about how much force there is on something, but also how much space or area that force is applied over. Okay? So if you get so I don't want to use that analogy. Okay, so when you're measuring pressure, what you're measuring for a gas is really how many collisions are occurring on the inside of that container, but also how much space the collisions are spread out over. So if I have a large box versus a small box, and they have the same amount of gas, which is going to have more pressure? The small box, right? Because I have the same potential force of collisions because I have the same number of molecules at the same temperature colliding with the same average speeds. But if I have more collisions because I have less space that those collisions are spread out over, I have a greater force that results or a greater pressure that results from that. So the Pascal is a common unit, and that is one of the units that's used by the computer software that you're going to be working with in the lab. Lots of other units for pressure, including bars, torrs, millimeters of mercury, atmospheres. So we're going to talk about some of these units. Most of these units we're not going to worry about. We're going to be focusing mostly on atmospheres and millimeters of mercury. So as we think about pressure, what measures the pressure of the atmosphere is a barometer. And the standard atmospheric pressure, which is known as 1 atmosphere, so the unit atmosphere is related to how much pressure gas in the atmosphere creates at sea level. So if you're sitting there in the room, right now, there's a barometer in the back of the room, and I can't really see it, but it's close to 760. I think it's 750. But that means that there's pressure from the gas particles in the room colliding with the surface of your body, creating about this much force hitting on you. There's also pressure on the inside of your body pushing out. Since those two forces are balanced, your body is neither expanding nor imploding. Thank God. Right? So pressure is something, there's always pressure pushing down on you if there's a gas around you. You want to keep that in mind. So how do we measure how much pressure that is? Well, the way a barometer measures that is by allowing a surface of mercury to be exposed to the atmosphere, and then the particles in the atmosphere hit down on that surface of mercury. So to make a barometer, you can take a tube and you fill it up with mercury all the way to the top. Then you take a upside down pan and you put it on top of that tube. Then you flip it over. And then you just lift up the tube a little bit so it's not touching the bottom anymore. And then the mercury flows out and fills up some of the pan. But then the mercury is still going to be, it's not all going to fall out. Some of it is still going to be inside the tube, right? So that's how we get this situation. Because we started with the tube completely full, there's no gas in here. This is a vacuum. And when I flip my system over and I allow some of the mercury to drain out, that creates a vacuum here. So why doesn't the mercury, which is pretty heavy, even as a liquid, why doesn't it all flow out of the tube? Why is the level inside the tube higher than the level in the pan? Why doesn't this all flow down until it's all at the same level? Isn't it all attracted by gravity? Shouldn't it be pulling it all down to the same level? Well, it's because of the pressure of the atmosphere. If you did this and there's no atmosphere, like in outer space, the mercury would come down to the same level that the liquid is in the pan. You have no pressure. Right? What's causing the mercury to stay in the tube is the atmosphere. There's pressure outside, particles in the air, and those particles in the air are bouncing around randomly, colliding, moving in this direction, moving in that direction. Some of them come in and hit down on the surface of the mercury. Those little collisions is what pushes the mercury up the tube. So all I have to do to measure the force of those collisions is to measure how high the mercury is pushed up. The more gas I have, the higher the temperature, the more they're moving around, the harder they're colliding, the more pressure created, the further up the tube the mercury goes, the higher the pressure. So when we measure pressure in units of millimeters of mercury, or sometimes centimeters of mercury, what we're measuring is the distance up this tube that the mercury is pushed by the force of the gas, right? Pressure is really force per unit area. So it could be like newtons of force or pounds of force per square inch or per square foot per square meter. When you think about the pressure in your tires on your car, that's measured in pounds per square inch, right? It's how much force is spread out per square inch or per area within the tire. Millimeters is not a unit of force per area. It's just a unit of distance. So if you think about that as a unit, if I'm measuring something in millimeters, I'm just measuring the distance it has. In this case, the reason distance is a measure of pressure because the pressure is what's causing that specific distance for the mercury to go up. So we can measure the pressure in units of millimeters of mercury or centimeters of mercury. Any questions about that? So 11.21 says, why is it that if the barometer reading falls in one part of the world, it must rise somewhere else? So the barometer reading is a result from the particles hitting down on the surface of the mercury and pushing it up. So from one day to the next, if you watch the weather and you pay attention to a barometer, you'll notice some fluctuation in the pressure. Why is it that some days there's less pressure? What could cause less overall force of these collisions so the mercury is not rising as high? So there could be fluctuations in gravity, but the force of gravity is pretty consistent around the Earth. If you change your elevation, there might be some small difference in gravity, but the force constant that's due to gravity is constant enough where it shouldn't be resulting in changes in the pressure of the barometer. Yeah, there could be temperature changes, right? So if I increase the temperature, I could have these particles hitting harder, increasing the pressure. What else? Right. There's basically a constant amount of gas in our atmosphere, but that gas flows around from areas of high pressure to low pressure. Right? The gas is constantly moving around on the Earth. It's not always evenly distributed. So if you measure a higher pressure on one day, it's probably because the gas has flowed more into that area and you have a greater concentration of molecules in that area. There's more particles. So with more particles hitting down, it causes a higher pressure. So if the pressure goes up in Ohio on a certain day because there's more particles in that area of the world, that must mean some other area of the world has fewer particles because the particles are flowing around. So the flow of the gas particles on Earth is causing more particles to flow into one area, causes a higher pressure in that area, but in another area that the particles flowed away from now has less particles, so the pressure goes down in that area. Right? So that's how that works. So other units for pressure that relate to millimeters of mercury are atmospheres and pascals. These are the ones we're going to be focused on primarily. I think in the software you're going to use in the lab, they use a unit of kilopascals. So what is the atmospheric pressure in kilopascals? Or how many kilopascals are there in 101,325 pascals? Well, kilo is a metric unit, so we can use a metric table for every kilopascal. How many pascals are there? Kilo is 3 powers of 10, so we put the power of 10 with the smaller unit, set it equal to one of the larger units, and we have 101.325 kilopascals. So these are, when you're measuring pressures in the lab, they'll probably be roughly around that pressure, because you'll be starting with air at room temperature, and it's going to be at the same pressure as the atmosphere around us, roughly. So 1 atmosphere is just defined as the pressure, normal pressure at sea level on an average day, and that's the pressure required to push the mercury up 760 milliliters up a tube. Another device you can use to measure pressure is called a manometer. The difference between a manometer and a barometer is that a manometer measures the pressure of a sample of a gas rather than the pressure of the atmosphere around it. So there's really 2 common setups for this. I got some gas. I want to measure how much pressure is in there, how much force that gas is pushing on things with, the inside of the container, the particles that are flowing around, how much force do they have. I expose that gas to a pool of mercury. So if there were no gas in this sample, gravity would pull this end of the mercury down, the same as pulling the other end of the mercury, and they would be level. That would be 0 pressure. But when I expose that mercury to my gas, and the gas particles are moving around and bouncing around in here, and it's sealed, the gas particles start to hit down on the surface of the mercury. That pressure causes it to move up. So the difference in height tells me the pressure of the gas. So I know the pressure of the gas is the height of that the mercury has gone up. The other design is slightly different. Instead of having this sealed with the vacuum inside, it's just open. So on the right-hand side, why does that setup have a smaller height than the one on the left-hand side? All right, if it's open to the atmosphere and I don't have a vacuum up here, that means air in the atmosphere is getting in here and it's pushing down, and the gas is pushing up. So now I have a competition. So the pressure of the gas is going to be equal to the height plus the pressure of the atmosphere that's pushing down on that, that's canceling out some of that. Right? So that's another way to measure the pressure of a sample of a gas. Slightly different design. Mercury is nice because mercury is not volatile, which means it doesn't really evaporate. So even if this is open, the mercury is not just going to start evaporating out of the surface of that. It'll just sit there. The mercury atoms are very large atoms, 80 electrons. The electrons really shift around a lot, so they create a lot of kind of London-type forces where they create a lot of partial charges to attract the atoms together really effectively, and so they're not really evaporating at a significant rate. Any questions about that? It's another reason why mercury is used in these devices as well as in these devices. So one is it doesn't evaporate, so I don't have to worry about the pool evaporating. I don't have to replenish it. 2 is it's very dense. So I don't have to worry about the gas permeating through the mercury and coming up in here and other gas forming in there. The mercury is very dense, so the gas, when it hits it, it just basically collides with it and bounces off, and that force of those collisions is measured. I'm not adding an extra variable where some of the gas is penetrating into the surface of the mercury. Downside of mercury is it's very toxic. Okay, so next time we are going to talk about more properties of gases. We are going to skip over the section 11.4. However, that doesn't mean I won't test you on 11.4. So the reason we're skipping over this is because the individual gas laws that are mentioned in this section are not as useful to solving problems as the ideal gas law is that's in section 11.5. So I'm not going to spend a lot of time on 11.4. I might ask like 1 or 2 exam questions from that section, maybe 1. So make sure you read that section and watch the videos related to it.